In Neuralink, electrons as thin as a hair are inserted in the scalp to interact with the electric energy surrounding a neuron. The signals are then transmitted to an app in a digital device. Liquid Wire is a startup based in Portland, Oregon, and it is using a similar approach to interact with the muscles of the human body. This is not a new technique. Electromyography, or EMG, is a diagnostic procedure used to assess the health of muscles and of the neurons that control them.
During an EMG, a needle electrode is inserted directly into a muscle to record the electrical activity in that muscle. EMG results can reveal nerve or muscle dysfunction, or problems with nerve-to-muscle signal transmission. The electrodes then translate these signals into graphs, sounds, or numerical values that are interpreted by a specialist in a clinical setting. A nerve conduction study, another part of an EMG, uses surface electrodes, a sort of electrode stickers applied to the skin, to measure the speed and strength of signals traveling between two or more points.
Now, what if you could monitor your muscles' activity without any wires, needles, or a visit to a clinical settings? And monitor your muscle activity just by wearing some comfortable garments. This is the mission of Liquid Wire. Mark Roney is the CEO of Liquid Wire, and he gave details about the technology during a keynote presentation at Semicon 2020, one of the leading events in the semiconductors industry. Here are the highlights.
So there what we want is an EMG that sits on the surface of the skin that a wearer can wear essentially all day. That can survive don and doff cycles and can be held in place by a very comfortable textile, so compression garment, rather than some sort of wet adhesive, which tends to break down the skin over time.
And this is what the complete design looks like once it is embedded in fabric. It is practically invisible, which really is the goal of Liquid Wire. The electronics disappear in the garments that they're placed into. So ideally the user is not aware of the electronics at all. The fabrics and electronics are kept together with a special sealant to protect all the circuitry, which makes the smart garment washable for many cycles.
And here we can see it actually in use with some of our engineers. We have two images here. One is one of our folks showing it conforming onto his arm. This is the potted circuit not yet laid up into a garment. Very robust. Again, they can be bent and flexed and stretched to a degree repeatedly with no damage. And then once they get laid up into a compression garment, they really do just disappear in there, and you can barely tell it's there at all except for a slightly thicker portion on the garment. That compression garment holds it tightly against the skin and allows the signal to be taken off repeatedly. You can see as he held it against his skin, it moves along with the muscle without digging into his skin or causing any kind of discomfort, and the electrodes stay in good contact even as his muscle flexes without the use of a wet adhesive.
The technology.
This is the core of our technology. This is what we call metal gel. So we take a alloy called gallium indium tin, which has been really well characterized academically as a fluid phase conductor for a couple decades now. Gallium indium tin was originally developed to be a non-toxic analog to mercury, both for use in thermometers, but also for stretch sensors and other liquid relay switches and the like. This has been widely used, like I say, academically, but it's never been commercialized because it's considered unscalable. So there's a real yield issue when you try to pattern circuitry out of this very low viscosity liquid metal. It tends to leak and flow all over the place. Our main innovation was to gelify it. So we put an inorganic binding agent that tunes rheology from about, say, like water to something a little closer to toothpaste. Once that's done, we can process it easily. We have a variety of printing techniques, and we can run it through different lamination machines to build these multi-layer circuits. Here we see the main material advantage of using liquid metal interconnect, which is that it does not fatigue. So once it's laid into a plastic and stretched, it flows along with that plastic substrate. There's no opportunity for tears or cracks or any kind of breaks to happen because the conductor itself remains fluid during operation. So you can stretch it for thousands and thousands of cycles and see no breakdown in connectivity. This is pretty important for a wearable, either medical or something that's going to be used in performance sports. We consider our main competitor to be silver inks, which are kind of an industry standard right now for a lot of wearables. Those inks, we have a graph here that shows kind of a comparison of how the inks fatigue versus how the metal gel fatigues over time. You can see on this graph on the side, this blue line that has a constant upward trend. This is a silver ink sample being put through a fairly gentle stretch test, just 50 cycles. And you can see this constant upward drift. So still functional after the end of 50 cycles, but the conductivity has gone up about 10x. In contrast, the red line at the bottom is our material. And that's really just a zoomed out version of what I showed on the previous slide. You can see performance is just dead flat. It never drifts up. It flows along with the substrate and then reforms when the substrate returns to its original length.
This is the circuit. In itself, is not that innovative. It's a fairly standard driven amplified filter. The main goal is to separate the noise from the useful information. So, let's skip to the applications.
So, here you can see a lot of the key features in our technology set, this interconnect and via system on a thermoset substrate. So this is again done in conjunction with our partner Panasonic, who provides the substrate material. This substrate is quite pliable as a texture. So if you do place it against your skin, it's quite comfortable. It feels, well, I'll say similar to leather. And then it can bond up into textile and into a general garment while hosting all these active components.
How it is made.
So this is the basic construction of the circuit. And to my mind, the most interesting part is we use a technique we call stencil in place, where we take each successive layer of the circuit and carve channels into it. These channels are masked, and then the conductor is placed into them. As I mentioned, the consistency is similar to toothpaste, so it flows under shear, but it stays in place once the shear is removed. This allows us to print, take off the mask layer, and then have the channel hold static while we laminate on the next layer. And it's built up in a piecewise fashion with the interconnect systems and then a via layer, and finally on top, a component layer where the components are adhered in place. But we're involved in a number of other medical patch devices for collecting other signals directly off the body. So an EMG circuit is really closely related to an EKG circuit. We can couple up with a lot of systems beyond dry electrodes. So temperature sensors, microphones, chemical sensors, pressure sensors. These are all devices that we serve as an interconnect for. And when you think of our technology set, it's not primarily around direct sensing. It's more about interconnecting third-party sensors or providing a packaging solution for electronic devices that is compliant and conformal and compatible with the human body.